Assalamualaikum. This is the Discrete Homotopy lecture series. So today's lecture is about I infinity is not a contractible. Okay. So let's define I infinity. I infinity is an infinite path graph whose vertices are integers and edges as like this ordered pair I to I plus 1 where I belongs to integers. If we draw this graph, so this type of graph 0, 1, 2, 3 and so on to infinity and -1 -2 -3 and so on to minus infinity. These are the vertices of this I infinity and edges. What type of edges? Edges are like I to I plus 1 if which I to I plus 1. Okay, so if we choose I is equal to 0, so 0 to 1 edge. If we choose 1, 1 to 2 edge, and if we choose -2 I, so -2 to -1 edge. Okay, this type of graph I infinity. So let's define I infinity is not a contractible. Okay, so there is a definition of contractible. A graph X is a contractible if there is a unique map from X to I0. What is I0? I0 is a graph whose on there is only one vertex 0, or we can say another X naught or anyone. There is an only one vertex and there is no edge. Okay. So there is a unique map X to I0 is an a homotopy equivalence, or in other words, there exists x naught belongs to xv. There is a vertex from xv and a graph map, constant graph map uh, from I0 to x such that g of this vertex, this is a vertex from belongs to this, we can get x naught. So such that id on x is a homotopic to cx naught means constant map. Okay, so let's define the proof. So let's say I infinity is contractible if and only if there exists x naught belongs to I infinity such that I infinity id on I infinity is a homotopic to cx naught constant map. Okay, at x naught. So cx naught is a constant map from I infinity to I infinity for all I infinity means cx naught of I is equal to x naught for all I belongs to I infinity vertices. Okay, or we can say integers. Let's define here. So we will prove by contradiction there is I infinity is not a contractible. Let's define the proof. Let's say I infinity is contractible. Okay, because the proof by contradiction I infinity is a contractible, then there exists x naught belongs to this vertices of I infinity such that there is a integer set of vertices and there exists a homotopy. H is a homotopy, or we can say graph map from I infinity box product with in to I infinity for n belongs to natural number union infinity such that h of 0, if we substitute in the place of this 0, so we will get I infinity id on I infinity means we will get I. So this means that identity of I infinity, if we substitute in, so we will get x naught for all I belongs to integers means this is there is a constant maps. So identity of I infinity is homotopic to. We have to prove identity of I infinity is a homotopic to constant map at x naught. So let's define. So first of all, define the box product I infinity to in such that the vertices set of this and this, the Cartesian product of vertices set of both. There is integer is the vertices set of I infinity and the vertices set of in is equal to 0, 1, 2, so on to n. Okay. So if we box product to edge set, so for horizontal, we will define this I to I comma j to I comma I plus 1 to j for all I belongs to z and j belongs to 0, 1, 2, so on to n. Okay, for vertical set of edges I comma j to I comma j plus 1, where I belongs to integer and j belongs to 0 to n. Okay, so let's draw the box product of I n to I infinity to I n. Okay, so if we go horizontal, so this type of uh, edges I to j and edge I to I plus 1 comma j. Okay, if we go to horizontally, so this type of edges I comma j to I plus 1 comma j. Okay, we can see 0 comma 1, 1 comma 0, 2 comma 0, 3 comma 0, 4 comma 0, and so on to 0. And if we go to left side, minus 1 comma 0, minus 2 comma 0, minus 3 comma 0, and so on. So if we go to downward, so this type of edges I comma j to I comma j plus 1. So 0 comma 0, then 0 comma 1, comma, then 0 comma 2, 0 comma 3, and 0 comma. If we go to this side, 1 comma 1, 2 comma 1 comma 0, 1 comma 1, 2 comma 1 comma 2, 1 comma 2, 1 comma 3, and so on to 1 comma n. Okay, if we go to left side, there is an changing in this I component. Okay, I minus 1 comma 1, minus 2 comma 1, minus 3 comma 1, and so on. Okay, this is the box product of I infinity to I n. Okay, so let's go again. Next step. So if we substitute h of dash comma 0, we get I, which means that the identity of I infinity for all I belongs to integers. And if we substitute the last step n, so we get x naught for all I belongs to integers, means x naught means c of x naught. This is a constant map at x naught. If we fix I, so j to I, h of I comma j is a path in I infinity. Means there is a homotopy from I infinity to I n. I infinity box product with I n to I infinity. If we fix an I, if we fix an I here, so we will get a path, we will get a path in I infinity in this from I to x naught, which is the length is n length. Okay, almost. So we can say I minus x naught is less than or equal to n. Almost the length is n, or we can say 0 or 1 or 2, and so on. But it should be hold for all I belongs to integers. If we choose I is equal to this, I is equal, if we choose I is equal to x naught plus n plus 1, so substitute I in this equation. So x naught plus n plus 1 minus x naught. So x naught minus x naught positive and x naught negative is cancelled. So we get n plus 1. So n plus 1 is less than or equal to n. There is a contradiction, means I infinity is not a contractible. Okay. So again, I explain in this part. So fix I, if we fix I, means this is I and this is j. So if we fix I, suppose I is equal to 0. If we fix this I, so from j to hij means there is a path of n length. Okay. So this is a path of n length. If we fix I2, so there is a path from this to n of n length, almost n length path in I infinity, means from this to this I2 x naught n length, almost n length, or less than n. So if we substitute I is equal to x naught plus n plus 1 in this equation, So x naught or x naught cancel. So we get xn plus 1 is where n plus 1 is not equal to not less than equal to n. So we get contradiction. So our assumption I infinity is a contractible is wrong. So this is our proof I infinity is a not a contractible. Okay, let's define again, shortly define. Prove by contradiction. Let's say I infinity is a contractible. So if a contractible, so there exists a homotopy from I infinity box product with in to I infinity for n belongs to this, such that if we substitute 0, we will get identity map at I infinity. If we substitute n, we will get constant map. So this I infinity is a homotopic to constant maps. Okay, so let's define the box product of I infinity in. So vertices are Cartesian product. The vertices set of this and this, the Cartesian product of integers and this. And if we box product with edge set, so there is an horizontal edges and there is an vertical edges. If we go to horizontal edges, we will fix j. If we go to vertical edges, we will fix I. Okay, so we can see this box product. If we go to horizontally left or right, so j is fixed 0 0 0 0 comma 0 1 comma 0 2 comma 0 3 comma 0, and if we go to left side minus 1 comma 0 minus 2 comma 0 and so on. So if we go to top to bottom, so I is fixed and j is change. So 0 comma 1, 0 comma 0, 0 comma 1 to 0 comma 2 and so on to 0 comma n. So this is the box product of I infinity I n. If we if we fix I, if we fix I, so j to I h I comma j is a path in I infinity. There is a path from this box product to I infinity. Okay, I infinity, there is a path from I to x naught is n almost n length or less than equal to n length. Okay, but it should be hold for all I, but there exists an I. There is an I. If we substitute x naught plus n plus 1 in the place of this equation according to the definition, according to the our uh, diagram, so we will get a contradiction. So define and prove I infinity is not a contractible. Okay, we will see in next video, next lecture. We will see next topics in next video. Allah Hafiz.